Good. Why was Santa's helper depressed?
Why was Santa's helper depressed, Rick?
Because he had very low self-esteem.
Oh, Rick strikes again.
Oh, that was so good, wasn't it?
Cheers to that.
Love it.
Cheers to that.
I love Christmas
Grab a tea.
We don't have
Tea
time
and
for
jokes.
jokes if you're drinking all the product. So
Oh,
instead you come up with a
that's
webinar.
why
this
it's
month.
here.
Yeah.
What are you guys doing? You guys told me this is okay.
I just have water.
I have tea.
Okay, well, let's get it together. Let's get started.
Okay.
Welcome everyone to December's webinar. It's a bit of a departure. We're not going to have any equations this month. It's going to be a little bit of fun to show you how to use our instrumentation, let you learn a little bit about it and how it works, and then also understand how you can use it in a very practical way. So something very relevant this time of year is you're going to have fun, you're going to be partying, whether you're celebrating Hanukkah, Christmas, or just life. One way to test your beverages to check for alcohol content is viscosity. Viscosity is very sensitive to the contents of ethanol. So we have a variety of beverages here today that our engineers who have agreed to join in and help are going to test for us, and then we're going to talk a little bit about the data and how you can make some sense of it. So let's quickly, in case you're not familiar with our technology, we have VROC technology, so viscometer, rheometer, and a chip. This is microfluidic viscometer, a bit different than your rotational system. I'm going to ask Nate, our service engineer, to show you what is the core technology of our system. So Nate, if you could show the chip to the camera.
Absolutely. So here's a look at the flow channels of the chip. We made it pretty close here. So you can see this is what the flow channel looks like. Is that turning out okay, Brandon?
Yeah.
Great. Fantastic.
Awesome.
So unlike the rotational systems, our technology is we're controlling flow rate through that flow channel. Beneath the flow channel are 4 pressure sensors. So we are measuring pressure drop across the channel. We can convert that to shear strength of the wall. We can convert our flow rate, which we are controlling, to shear rate, and we calculate viscosity. So now that you've seen the flow channel, you've seen how tiny it is, and knowing the fact that it's enclosed within this unit here, which we refer to as a chip. It's ideal for this type of measurement because alcohols are volatile organics. So if you're working with an air-fluid interface, you're going to have constantly changing data unless you're controlling for that evaporation. And then also it uses clearly a very tiny volume, and you don't want to waste your product on your testing, but you do want to test. So we're going to get into it, and just a quick other tip. This is more of our lab research level instrument. However, we do have a portable instrument with a rechargeable battery and disposable pipettes. So if you need to test on the go, if you don't trust your friends, you can take this with you and test, again, very small volumes while you're out and about. Okay, so we have a variety of beverages here. We're going to start going through the testing, and the engineers are going to talk to you about how to do the loading, and you also see the software in action, and you'll see the data coming up live, so you can see how the instrumentation and the software works. And just one quick tip too, when you're dealing with certain beverages where you're adding flavorings like nutmeg, cinnamon, things of that sort, these are large particulates. So remember, we're working with microfluidics. So that we don't clog up the channel, it's best to do some filtering to get that out. So this is simple to do. It's very easy. You can just load your syringe with your sample and then pass it through the syringe filter into a vial and then load it up into the test syringe. So we always recommend that when you have particulates such as the nutmeg. Okay, so I think we're going to start with Nate. He's going to start with everyone's favorite seasonal beverage.
Yes.
And I'll step out of the way and let him get started.
So first, before we get down to business, I want to make sure we're taking the proper precautions. So we're wearing our PPE here, so I'm just going to put on some gloves really quick.
Great sound.
All right, so now we're ready to go. So as Stacy was saying, the first beverage that we're going to be testing today is pumpkin spice latte, more commonly known as a PSL. So we have our pumpkin spice latte
This one.
here. I think is that. So here it is, PSL. and as Stacey was also saying, we did filter these. So it's not going to be the exact composition that you would find in the bottle. So with that in mind, we'll go ahead and start loading it. So the first thing you're going to want to do is load the sample. Of course, we've already loaded them. And the next thing you want to do is, and also just want to check the bubbles. If you do find bubbles in your sample, they're pretty easy to remove. You could just tap the syringe until the bubbles float to the top. Once they're at the top, you can just push the bubbles out by pushing on the plunger and then just cleaning up what's left on the thread. So once you have your syringe ready, you can go ahead and grab the chip here. So the chip right now has this plug in it. So this is just to prevent anything from getting into the chip when you're not using it. So we'll go ahead and take this plug out. Okay, so I've taken the plug out now. So now go ahead and take the syringe, and you can see there's threading on the end of the syringe here, and there's threading on the inside of the inlet. So I'm going to go ahead and place the syringe into the chip and just thread it in. Okay. So now I'm going to place the chip and syringe into this syringe jacket here. There we go. Okay, so also I just want to mention, since we're working with microfluidics and very sensitive sensors, the pressure sensors can be subject to damage if there's an unexpected pressure spike in the chip. So you just want to make sure that you follow this order of operations whenever you, excuse me, load sample into the instrument. So the first thing you're going to want to do is move this pusher block to the end of the plunger. So once the pusher block is contacting the end of the plunger, you're going to go ahead and pull this knob out and rotate it. So once the knob is rotated, you can see it can't move this pusher block anymore. So what that does is it protects the plunger from being accidentally pushed and causing a pressure spike in the chip. So once this pusher block is locked into place, I can now open up this valve. So when this valve is in this position, no liquid can get through. So I'm going to go ahead and open it. So now you can see the valve is facing forward. So now sample can freely flow through the chip. And the last thing we're going to do is just go ahead and close up this syringe jacket. So close it, and then there's a screw here that you just need to thread in. So once the syringe jacket is closed, we can go ahead and start the sample testing. So Brandon will go ahead and do the honors.
So the first thing I'm going to do is we can push the pusher block until it hits the end of the syringe. The instrument knows automatically when it's reached the end of the plunger. And then afterwards we can run our measurements. You can see we have sample ID, pumpkin spice latte, and you can put in an estimated viscosity if you have one, and it will give you parameters to run your sample at. We decided to do a fixed flow rate of 300 microliters per minute. And so we saw that it hit the plunger, detected it, told me that it was ready, and then we can click start. It'll go to the data graph page, and then once it loads up and is ready, it will start to pump the sample through. It first takes a baseline for the pressure sensors, and then it will move, and you can see it loading up now. We have a couple different graphs if you're unfamiliar. There's the viscosity versus time graph that shows us the live feed of viscosity as it's running through the chip. It did one measurement, and now it's doing a second one. You can also see the 4 pressure sensors, the pressures that each of them are reading at any given moment. And that gives us an R squared, which is how well we can tell the pressure curve is. And then right now it was 0.997, which is pretty good. And we got an average viscosity of 1.684 Santa Claus.
You were just waiting to say that.
Mm-hmm. All right.
So now that the testing is complete, we can now switch our samples. So first step is to move the pusher block away. So, well, actually, excuse me. First step is to open the jacket and then close the valve so that we can't accidentally overpressure the chip. And then we move the pusher block back. And then we can remove the syringe gently. And then, so my sample is everyone's favorite holiday beverage, whiskey. And there's a little bubble at the top, so I'm going to remove the bubble carefully and use a lint-free wipe so I can then brush off any residual whiskey and some dust or potential dust so that there is no dust or bubbles that enter our chip. And I will load the sample. Again, it's threaded so it can have a nice tight fit. And I will gently place it into the jacket. And again, this valve is closed, so I won't risk overpressuring the chip. Gently, I might have to wiggle it around a bit, the pusher block. Lock it into place, and then open the valve, close the jacket covering, and screw it on tight.
Quick comment before we move on. So you'll notice we didn't clean out the chip prior to moving to the next sample. So if your samples are all soluble and you feel that you can flush the previous sample out with the next one, then you can skip the cleaning step. But always bear in mind that you need to confirm solubility of samples first if you plan to operate this way.
Thank you, Stacy.
So I just pushed the pusher block forward until it hit the syringe, and now we can start the run. I added a couple extra measurement steps to help flush out any of the previous sample, and then the last measurement will be hopefully our rye that we're testing.
I love the sound of science.
Put you in a festive mood.
Oh, yeah.
So we had our first measurement, and that pushed out, and you can see there was a significant change from when it went from our first sample up the size latte until it jumped up when it hit the whiskey. So we got a nice flat line here for our pressure scale, and we can see that by the R squared, which is 0.997, and we had an average viscosity of 3.78.
All right. So I just have to say I'm really excited to do the next sample. We're doing eggnog.
Rick strikes again.
Oh, you know it. All right. So as before, we always, I'm just going to move some stuff around here. Open up the syringe jacket. Close the valve. Now we can move the push block. And so at this point, we can safely remove the whiskey. And what we'll do next, or what I will do next, is test eggnog.
Sounds excellent.
Excellent nog.
Excellent.
And sometimes with higher viscosity samples, if you have a bubble, and it doesn't move up into the opening of the syringe, there's a special technique that you could do to remove the air bubble. And how you do that with higher viscosity samples is you hold the plunger with your index finger, and then with your middle finger and thumb hold the barrel of the syringe and flick it in this manner. And so that will force the air bubble to the opening of the syringe, and then at that point you could just push it out. So I will clean off the tip of the syringe to make sure no dust has contaminated it. And load this in. Move the pusher block. Open the valve. Close the syringe jacket. And we are ready to go. So Brandon is using our software to push the block until it contacts the plunger. Our system knows when it's contacted the plunger by a pressure drop in the flow channel. So what we're doing now is we are doing a sweep, basically, and the first run of the sweep is a purge step. And so we're using the first step to remove the whiskey and replace the contents of the whiskey with the eggnog.
There's a waste port here where you can actually see the changing fluid in real time. So this is the last drop of whiskey, and now we're switching over to eggnog.
And you can see on the graph, if you have different samples, you know, sometimes you may have samples that are very similar in viscosity. And so it looks like that might be the case with what we're seeing now. But we'll see at the end after the viscosity runs out. Okay, now we've completed a rate sweep. Data is being saved, and so you can see you can do a rate sweep really quickly and easily. Other systems don't have our capability or software to handle this type of analysis. Another advantage of having a RioSense viscometer in your lab.
But we can see that, again, we got a nice measurement. R squared looks good, 0.998, nice flat curve. And we got an average viscosity for our last reading of 1.966.
All right,
Looks
so
good.
the next step is we are gonna dial up the fun a bit with eggnog and rye. Okay. And so what we've got here is we have 20% rye whiskey with eggnog.
Trade.
We'll just blow off the tip of the heads. And this is an important step to make sure you're not introducing any dust or lint into the microfluidic channel.
And this way you can tell if your teenagers have gotten into the liquor cabinet.
That's right. Viscosity, you can't lie.
Yeah. So the rye was 2.5 centipoise or centipoise.
I believe we're around there. Yeah.
So what will the viscosity of whiskey plus eggnog be? We're about to find out. Viscosity doesn't lie.
Viscosity does not lie.
So-
Yes, go ahead.
Oh, so again, we're just gonna push the pusher block forward until it contacts, and again, the instrument will let us know.
And so we're running the same type of sweep where the the first shear rate or the first segment will push out the eggnog only, and then that'll be replaced by the eggnog and rye mixture.
So we can see like this nice first curve, and then there's a dip, and then another plateau. That's a good sign that this was the first sample, getting the last bit of the first sample that's left in the channel getting pushed out until the new sample is going through.
And again, this is all done automatically. Once you set up your run, hit go, and then you can walk away and come back to your data.
What's it looking like?
It's looking pretty good. We have a nice R squared of 1, which doesn't get any better than that. Interesting enough, we have a higher viscosity than either the rye by itself or the eggnog by itself, with 2.933 centipoise.
Oh boy.
It's getting rough.
Yeah, it's getting rough, huh? So again, I'm gonna open up the jacket, close the valve, and move the pusher block away.
Okay.
You can exchange sample.
All right,
So
so
what's next?
Next sample are my 2 samples. We got 2 different types of wine. We have a kosher wine that states that it's very high in sugar, and then we have a Cabernet wine that we're going to test. So, thank you. Again, make sure there's no bubbles, and then we want to clean it off. We always use lint-free wipes to make sure that there's no fibers, but even so, we always make sure to air dry everything off, make sure there's nothing left.
Someone's jingling around.
Oh yeah, I got some bells on me. All right, so just like before, we can push the pusher block forward, make contact with the plunger, and then we can start our measurement.
So the kosher wine has more sugar in it than
Yes,
the
it
regular
states that
Cabernet.
it's a specially sweetened wine. And so we're doing our first flush through. Again, we can see this nice bump from the last sample that was still in the channel, and now we can see our new sample being run through.
So again, I just want to reiterate that before we ran our samples, we tested them all for miscibility, which is why we're not cleaning in between. But this isn't always the case. So if you are doing viscosity testing and you are going to run one after the other, make sure that they are miscible.
So the data's looking pretty good. The first flush through went through, and this was the last measurement. Again, have a perfect R squared for the curve of the pressure scale of 1. And we have an average viscosity of 2.613. So we'll see how that compares to the Cabernet.
Closed.
Yeah. You can look at it, right?
that bubble in there. Just want to remove that really quick.
Oops. Merry Christmas.
Merry Christmas. And Mazel Tov.
Mazel tov.
Thank you, Zach.
Testing too much of the sample, were you?
My face is turning about the color of that sample right now.
Well, that's what happens when you go live.
Yeah, that's what happens when you do it live. Let me fish the table back into.
Clean up my desk,
What
please.
what else is in that?
Lots of pumpkin spice latte.
Oh,
Or the PSL,
that's what
sorry.
he said.
Oh, a lot of spices in there.
Nice and spicy.
Nice and spicy, huh? Push your block. Lock it. Open the valve. And then secure the jacket.
Well done.
Yeah. It's like I've been doing it my whole life.
All right, plunger's been contacted, so we can start our run.
So another cool thing that you could do with our technology, aside from rate sweeps, you could also do temperature sweeps. Very similarly to how you would do a rate sweep. You can just plug in the temperatures that you want, and the system will automatically go to those temperatures, stabilize for 2 minutes, and then we'll run the test. And this is all done unattended. So it frees you up to do more important things, like
Test your samples.
test your samples, have some eggnog, whatever you want to do.
Yeah, go to lunch.
Sit by our fire.
Tell some good Santa jokes.
Oh
Yeah,
yes,
Santa jokes.
they're so exciting.
Comment on our ugly sweaters.
Feel free to let us know who you think is the best.
Yeah, who has the best sweater?
Yeah, I just couldn't go there. I had to go with the blazer.
Rick is too fancy.
All right, so it looks like the Cabernet finished. Again, nice R-square, 0.997. Interestingly enough, the viscosity went down to 1.372. So I think we have our in-house rheologist that can go over some of the data points that we got.
Okay, thanks for all the testing. So just once you've collected your data, it's always a good idea to take a look at it and think about it and say, does this make sense? Because we always like to point out to people that viscosity is not a directly measured property, it's calculated. So things can go astray no matter what type of instrumentation you're using. And we always like to look at the data and see what we can extract from it and does it make sense. So because many of our beverages had some alcohol in them, and then also our NOGs they're not unfortunately homemade pure products. They're commercially manufactured, so that means they're going to have some thickeners in them. So there's going to be some high molecular weight edible polymers like locust bean gum, something of the sort. So you have some interesting ingredients that you want to think about also in this type of sample. So I jotted some of the information down as everyone was collecting the data. So the pumpkin spice latte kind of stands on its own in about 1.4 cents per. So that's probably reasonable. It's predominantly water with some probably a tiny bit of thickener, some flavorings. That makes sense. So now when we move into the drinks with alcohol, I sort of quickly sketched out a plot here that we're going to refer to. So this is viscosity as a function of percent ethanol content. Alcohol water mixtures are interesting because although the viscosity of pure water and pure ethanol are pretty close, off by maybe about 10%, when you start mixing them, you get this peak and then a drop off instead of having just a nice line connecting them. So there's once you start mixing them, the way the water and the ethanol interact, it's not ideal, and it gives you some interesting behavior. So This is out there in the literature. In fact, we have an application note on this. If you want to go to our website, little plug, you can download real data instead of just looking at my drawn curve here. But we're going to refer to this when we look at some of our samples. So the rye whiskey that we purchased was labeled as about 45% alcohol content, and the viscosity is coming out at about 2.5 centipoise. So yes. So I was trying to draw this to be predominantly realistic. So if we look at about 45% alcohol, that is coming out to be about 2.5 centipoise. So we did get our money's worth here, and that seemed to be a realistic value for that particular product. Now the eggnog, when we measured the eggnog, this too was coming out at about 2.5 centipoise. Again, the eggnog, although predominantly water-based, it does have some fats, some proteins, and the added thickeners, the locust bean gum, gellan gum, or if you look at the ingredient list. So this seems like a reasonable number. We can't really say too much more than that at this point. And then because the best eggnog has a little rye added, we did that mixture at 20% of the rye whiskey. And in this case, now the viscosity comes out at 3 centipoise. So this is kind of interesting. You're taking two things that are about the same viscosity and mixing them together, and you get something higher. So at first glance, that seems a little odd, but again, thinking about the fact that we have alcohol-water mixtures in play, that's going to influence it too. And then also, when you have these larger macromolecules like the locust bean gum, as soon as you their interactions are quite significant, and when you change the environment by adding the alcohol, you can change how they structure, whether they expand or collapse, and how they interact with each other. So this is not beyond the realm of possibility. This is coming from the changes in interactions that you get when you mix the alcohols and then change the environment of these macromolecules. So it's not too unusual. I'm going to jump to the Cabernet before I get to the sweet wine. This one was coming out somewhere around 1.4 centipoise. Again, we know from the bottle that this is about 14% alcohol. So if we look at our roughly sketched curve here for viscosity versus ethanol content, that's about reasonable for that alcohol content, given that other than that, it's predominantly water-based. The kosher wine, however, which is only 11% alcohol, so less there. So if you're thinking about just alcohol content, you'd think the viscosity there would drop. But this one is actually significantly higher, about 2.6 centipoise. However, when Brandon was measuring this, he did mention that it's highly sweetened. And so that's another thing to consider. When you add a lot of sugars or corn syrup in high levels, this will increase the viscosity significantly. So likely, although it has lower alcohol content, it has a lot more sugar than Cabernet, so giving you a much higher viscosity. So we always like to recommend when you get your data, look at it, think about it in the context of what you know is in the system and how those components are behaving, and make sure everything is kosher. So I think that's about all we wanted to share today. We wanted to show you the instrument, talk about how you can use it to measure samples at this time of year, show everyone our engineers that you may talk to on the phone, exchange emails with, but not see in person. You can see their taste in Christmas sweater as well. And we can see if we have any questions as we wrap up.
So we have one question so far. What is the rule of thumb for the particles? I assume they're talking about particle size.
So it's dependent upon the chip depth, correct?
Yeah, you want to make sure that the particles in your samples are less than 10% of the channel depth. So we have flow channels ranging from 20 microns up to 300 microns. So if you have different needs in that respect, then you can handle that. But yeah, 10% or less of the channel depth. And we do have a range of channel depth depending on your needs. While Brandon is looking at the other questions, I'll point out, in addition to varying channel depth, we have various scales for the pressure sensors. So all of our beverages, as you saw below, on the low end of viscosity in the grand scheme of things. So we were using our most sensitive chip with the lowest pressure range.
We have another question. Can you tell the difference between high quality wine and low quality wine?
Well, I guess it depends what you consider low and high quality. I think some people would really enjoy this very sweet wine, whereas others would consider the drier Cabernet the higher quality. So you can tell the difference in wine depending on the alcohol content and the sugar content, predominantly. Those are the big factors there. So I guess we'll sort of leave it in that more objective fashion. As good and high and low is probably more subjective.
One thing you can do is you can use viscosity as a way to feel what you're drinking. For example, mouthfeel has a lot to do with viscosity. The more smooth, the more silky a beverage is, you can see that viscosity may tend to be a little bit higher because of whatever was added to that. Whereas something like water, where you don't have that smooth texture, it's very crisp and clean, that tends to have lower viscosity. So you could use that as a way to formulate, for example, different beverages to elicit a certain feel.
So like the additives that we discussed in the purchased eggnog, which had the thickeners, which is common in a lot of natural beverages. So that would change viscosity and
Exactly.
Another question we had was, how can you use viscosity values of wine in a QC environment? A good way is you can always test viscosity of your sample as it goes through different processes. If the value is not consistent batch to batch, you can tell if there's any differences. Again, like if there was the incorrect amount of sugar that you wanted, this would show up the incorrect amount of alcohol percentage. This can all be indicated by measuring viscosity.
And I can't see the questions, but I'm sure this question was asked. And I got this sweater on Amazon.
Another question we have is, we had someone ask, can the machine handle thicker consumer products such as lotions, creams, shampoos?
yes, the answer is yes. So as we sort of hinted at earlier, or just a few moments ago when we were talking about the particle size and the viscosity range that we were testing, we do have a very broad range of pressures that we can access. So if you're dealing with something in higher viscosity, you'd want to choose perhaps a deeper flow channel and then a less sensitive pressure sensors. So higher pressure range that you can access. So you can go much higher in viscosity. You would just use a different chip than we used for the relatively low viscosity values.
Yeah, we've actually tested viscosities in the hundreds of thousands, Santa Claus range. For example, I think we've gone up to about 300,000 centipoise, which is 30 times the viscosity of honey. So we can get very high on viscosities.
Another question we got, will chem wipes work with your system? We always recommend not to use chem wipes. We find that although they say they're low in fibers, we've had multiple customers that have fibers because they use chem wipes. We always recommend lid-free wipes, and then also air drying off anything that's going to be touching any of the sensors or sample or anything like that. But I think that's all the time we have for questions. If we didn't get to yours, we'll send you an email explaining everything and answering any questions you may have. But I think for now, that's it. I hope you had a wonderful time, and we'll see you next time. Happy holidays.
Happy holidays.
Happy holidays. Thanks for joining.